Okay, today I'm going to talk about the isomerism. And isomers are substances that have the same formulas but differ in their structures and in their properties. Types of isomerism or isomers can be described into two broad categories. Structural isomers have the same number and kinds of atoms, but they differ in the structural formulas. Types are ionization isomers, hydration isomers, coordination, linkage isomers. So these belong to the structural isomers, where we can look at the ionization, hydration, coordination, linkage. So if we take the stereoisomers, number and types of atoms and bonds in molecules are the same, but certain atoms are oriented differently in space, and chirality is involved. Stereoisomers are geometrical isomers, optical isomers. Okay, so the stereoisomer, every time we talk about isomers, it's you have to produce or introduce two or more than two formula, and these formulas we can draw the structure and see how they changed. So sometimes we need a drawing, sometimes no, you just look at the formula of two and more than two compounds and you can decide these are isomers. So isomers, we need to have compounds, 2, 3, more. So the famous ones, you have like two compounds and then we compare them and to see the difference in the structure. And of course, there's a difference in the properties. So what's the properties? Physical and chemical properties. And the structure, you need to show the structure, how to draw the structure by using just Lewis sticks. And this is the most famous one. So if you have stereoisomers, you look at the geometrical and optical. So we need to have the coordination complexes isomer. Coordination. Okay. Well, let me put it down here. So if we look into the coordination complexes, isomers. So isomers, same atomic composition, but different in structures. Let's have a look. Different composition. So to the left is you have ionization, isomers, and you look into the structure, hydrate, linkage. Okay, wait, you come from the top. So we have the same atoms, is a different composition. If no, so you don't have anything. But if yes, you have isomers. And the isomers, I'm looking from the top till down. So same atoms, yes, we have isomers. And we can come to the atoms linked to the same partners. Yes or no? Atoms linked to the same partners. We come to the no, to the left. So you look into structural isomers. These formed or separated into ionization, hydration, linkage, and even coordination. So if you go to the yes, atoms linked to the same partner, you look into the stereoisomers, and then you come to the complex identical to its mirror image. If yes, you have geometrical isomers. If no, you have optical isomers. Okay? So isomers, ionization, anhydride, linkage, coordination, geometrical, cis, trans, optical, enantiomers. Structural isomers, let's look into ionization isomers. So they differ in an ion bonding to the metal. Let's see. So this is the compound, and let's see to the B. So now we have similar composition, similar atoms, but we have the formula is different. So the formula here, if you look at the A, there is brackets. Inside the brackets is the complex. Outside the brackets, you have chloride counter ion. But the second one, B, compound or formula, you can see you have a complex inside the brackets, indicated chromate, chloride, amino group by 5, but outside you have SO4, sulfate. So if you look, what are these? The A complex, you have a minus chloride. So the bracket or the complex become what? A cation. Or so you have anion outside, you have a complex of cation. So what is the charge on the cation? If you have Cl outside, it means minus. So the complex in brackets all will be +1. Compound number B here, you have outside SO4. What's the charge? Oxidation number of the SO4? It's -2. So the complex in brackets will be +2. So now you have ions. You have an ion, SO4, Cl minus, and you have cations, the complex itself. So how can we need to write the name of it. So first, when you have the complex here, you start with alphabetical, as we said, the nomenclature of the complex. So you start with the alphabetical one is the pentaamine, amine. So it's 2M, pentaamine, sulfato. So we change the sulfate to sulfato because it's a ligand. And chromium. Why I said chromium, not chromate? Because the outside, we have a cation complex. If there is a plus on the top, let me do it here. So this one, you can see here, when you separate the complex or the compound, you separated, there is one minus here. Okay. So it's a minus here. So the bracket should be plus. Now, so you have a plus. So when you have a plus here, you leave the element, the metal, as it is, chromium. Okay, if you have a minus here, it will be chromate. So now penta, amine, sulfato, chromium. What's the oxidation number here? So there is 2 minuses here, 1 plus here, it means 2 minus. Being taken 2 electrons from the chromate, so the electron lost 2, the chromate. And we have a plus here already been taken from the chromate, so 3 times 3 electrons being taken or removed from the chromate. So SO4 is minus 2. Where get the 2 minuses, 2 electrons from the chromate? So here already lost one originally lost, chromate lost 1 electron. We're ending with chromium 3. We leave space, and we write chloride. So counter ion, we will leave it as it is. We don't change the name of the counter ion, as it is. Now we come to here, inside. So as you see here, there is, if you separate, so if the SO4, what's the SO4? SO4 is minus 2. So SO4 is minus 2. And the complex will be plus 2. Now, what does it mean plus 2? It means the chromate, the chromium lost 2 electrons. Do we have another lose? Yes. Chlorine, when it's bonded to the chromium, it will take 1 electron from it to come back and donate a pair of electrons as coordination compound. So now chromium lost 2 electrons and lost 1 here for the chromium, for chloro lost 3. So the chromium will be 3. Still, we say chromium because of the cation on the top of the complex. Outside is a counter ion. This is a counter ion. We just call it sulfate. No change. We leave space. You should leave space. So we name the complex now penta-amine chloro chromium 3 space sulfate. So now these two are ionized compounds. Ionized means ionized isomers. They are similar number of atoms, but they differ in the structure. And they are ions. This is an ion, this is cation, an ion, cation. So when you have ionic compounds, this look like NaCl, NaCl, Na plus, Cl minus, ions. So here you have Cl minus and a complex. So now if you see here the this and that one, if you see outside the counter ion is halogen, so you straight away say this is ionic compound, ionic isomers or ionization isomer. So ionization, you can name now what is the cobalt here. So minus, plus, minus to the bromine, plus to the cation of the complex or coordinated compound. So now you name it. First, we need to know the oxidation number of the cobalt. Because of bromine, lost 1 electron. Because of Cl, lost 1. So the cobalt lost 2 electrons. One is giving to this bromine, the other one is giving to the Cl. So we have cobalt 2. And then now we name. So is it first you name the bromo or amine? You call the amine first. So penta-amine, alphabetical. Bromo, cobalt 2, space, chloride. Here, similar thing, cobalt oxidation number is 2. Now, penta-amine, chloro, cobalt 2, space, bromide. I call it bromide, no change. Now we come to the linkage isomerization or isomerism. Linkage. Well, what does it mean? Link. Which atom is linking to the central metal ion? Which one? So if you see a ligand or a molecule have two sides to link to the metal ion center, two sides, either from oxygen or nitrogen. You can see here, nitrogen is linked to the central atom. Here is oxygen. So NO2 is acting two sides, and it is a linkage ligand. When you have a link to the central ion, and we have two compounds here, you can name and see. So this compound originally is cobalt chloride nitro NH3 by 4, and it's a cation. So when there is a cation, you just leave space and ion at the end. Now we come here inside and see what's the name. So you call it tetraamine nitro. Okay, tetraamine chloro nitro cobalt. Oxidation number here is 3. How? NO2 is -1, Cl -1, and here. So the cobalt lost 3 electrons to give 1 to the chlorine, 1 to the nitro, and here as well from outside lost 1 electron. So in total will be 3. Tetraamine, chloro, nitro, cobalt. 3 space ion. We come to here. Now, what you have here is NO. What does it mean? It means being linked from the oxygen. So in this case, we call it nitrito. Nitro, when it's linked from the nitrogen, but from the oxygen, we call it nitrito. Similar thing. So the name will come as tetra. You have a tetraamminochloro, nitrito, cobalt, 3 space ion. And you can see here, what's that? So we have here is, this is it. So we can exactly do the compound, the formula should be like this. Either if you don't have structure, you can write it like this. Cobalt, NO2, close the parenthesis, NH3 by 5. And here is cobalt ONO. It means linked via the oxygen and left like this. Linkage isomer, another one is via the thio. Is it from the thio or from the carbon? We can see bonding to metal ion may occur through the thio from the nitrogen. So this is isothiocyanate. Isothiocyanate. So bonding occurs from the N atom to metal. And here you have NCS. If you have NCS, it means the link, the bond via nitrogen. If you have SCN, it means the S is bonded to the cobalt. So it's different. Thio, cyanide, cyanato, or you have isothiocyanate, isothio. And the name, you can write it down to see for this compound or for this. So what's the oxidation number here? For the cobalt, you have 1 minus here, and 2 pluses here will be 3. So the cobalt 3. Similar here. Hydrate isomers, it means there is a water in the coordinate sphere. There is water, water, water. So what we do, there is a counter ion here, Cl3. There is a Cl2 and H2O as outside counter ions. We have Cl2H2O as well. So we leave a dot between them. Okay, when just to separate the Cl2 from the H2O, you cannot leave it as Cl2H2O outside. No, you have to leave a dot. And you can leave a space as a counter ion. Always a space. So now water in outer sphere, cold water, named as hydrate. Water in the inner sphere, you call it aqua. Okay, so now this is the water outside coordination. Here the water is bonded. So once the water acts as a ligand bonded to the metal center, we call it aqua. When it's outside the atmosphere, so it will be hydrate. Now we come to the coordination isomers. So different metals with the same oxidation state. This is the coordination. All oxidation number divided on both metals. This is belong to the structural isomers. So for isomers like here, you have two compounds in one complex. So you have this minus charged is not related only to the chromate, but it's related to the both metal centers. So whatever you have charged here, you have to divide it on chromate and cobalt. So amine is neutral, but the cyano have -1 times 6 minus 6 divided by 2 chrome, each will take oxidation 3. So now when you want to name this, you have to go with this. The charge here is in minus. So this chrome will be chromate, but the charge here at the top here will be plus, and the cobalt will remain as a cobalt. So now you name it. Hexaamine cobalt 3 space hexacyano chromate 3. Here, what you have, CN, cobalt chromate, similar thing, but you have changed it to the left side. See, the chrome was with the CN. Now the cobalt is with the CN. What you do is you divide the -6 on chromate and cobalt, and here you have a minus charge, whereas here will be plus charge. So the chrome will be chromium, but the cobalt here as a minus charged will change to cobaltate. Hexaamine, chromium 3, space, hexacyano, cobaltate 3. And you can practice this as well, similar thing. You have a CN here, and you have CN5. So you can divide the 6 of them to be cobalt 3, chromium 3. And again, you have to see the charge here is more minus, and here is less. You have another one, similar here as well. Same metal with the same oxidation states. So we have same metal, same oxidation state, and you can see these are isomers. Platinum for amine, platinum, and you have 4-chloroplatinum. Here what you have platinum 3, and there are chloride inside, and the 3 chloride will be outside and NH3. So you can see here platinum always possess tetrahedral. Platinum is tetrahedral, similar here. Same metal with different oxidation states. Same metal. So this is the metal. When you have 6 chloride, you divide it. You divide this 6 on both platinum. And you have here chloride 4, and you have inside here chloro 2. So here you can see the similarity in the formula. Coordination isomers as possibly only for salts in which both cation and anion are complex ion. The isomers arise from intercharge of ligands between the two metals centers. Geometrical isomer. So now we have a geometry cis and trans, and it's for the square planar. You can see here, if you have opposite atoms bonded to the metal center, it will be trans. If you have a neighboring similar groups, either all of them neighboring all or at least two atoms, they are neighbored. So chloro-chlor, one beside one will be cis. So you have cisplatin here, diamine, dichloro, platin, oxidation number 2. So cis, and here we can call it for this one will be cis diamine dichloro platinum 2. And here you have trans, you have to put trans in front of it, and there is a minus, and it should be one word. There is no space between them. So it'll be trans diamine dichloro platinum 2. So when you have geometrical, you think about cis and trans, and we have another isomers as well. So now if you take the platinum NH3 by Cl, so you substitute another Cl, replace NH3. So here you don't have isomer. Here you don't have, if you change even the position, so it should be at least like similar atoms in one formula. There is no isomerism here. But if you come here and you replace NH3 with another by Cl, you end up with 2 Cls, 2 NH3. So either you put them one beside one, or one opposed to each to the other. And now you have isomer as a cis and a trans. So substitute the third chloride, you will end up with this. There is no isomers here, because like you don't have two atoms similar. So we have to have at least 2 atoms. So don't see 3 atoms. So in all case here, and here, they are one beside one, one beside one. So I cannot differentiate between this and this and say these are isomers. No. So because if you rotate whichever you rotate this structure, it will end up with the similar to that one. So this is this one. Similar. I don't have other compound. There is no difference between this and this. How one might differentiate, wait, this is wrong. Should be differentiate T. How one might differentiate between geometrical isomers, cis and trans. So you can use the dipole moment as cis isomer dipole is equal to 0, cis, because it's one beside one, so it will be 0. In physics, there are several kinds of dipole. Electric dipole is a separation, positive and negative charges. So we have south and north dipoles. These are the poles. So there are two, we say dipole. So how can you differentiate between cis and cis, cis and trans? You can use the outer magnetic field. If it is not okay, repelled, it will be cis. Repelled, it means just don't go inside the outer or alternative magnetic field. So it would be cis. Dipole moment, we discussed this before. So this is a dipole when there is two electrons, or we have one electron have north or south poles. Simplest example of this, a pair of electrons, equal magnitude but opposite spin, opposite sign, separated by some usually small distance. A paramagnetic electric dipole is called electret. H2 has a dipole of partial charges like plus, half minus. So they are partially charged. And you can see the change here as well with the ozone. So you have here this and that will be what dipole moment will be 0. HCCl remove each other. So here, if you see the dipole moment will be 0. Why? Because CCl remove CCl, CH remove CH. So dipole moment will be 0. Whereas here, trans, when you have a trans here, there is a dipole and everything is changed. You have magnetism here. Okay, so sniff reaction. You can differentiate between cis and trans by using sniff reaction. What's that? Addition of symmetry bidentate ligands, such as oxalate, will react only with cis isomer. No reaction with the trans. Okay, so you can add bidentate ligands. It will react with the cis isomer, but with the trans, no reaction, because symmetrical ligand can take the cis place only and not the trans position. So you can see here, if you, this is a cis plus oxalate, you add oxalate to a cisplatin here, you can see there is a reaction replacing the chlorine by oxalate, and the chlorine will leave as a gas. But if you add trans isomer of this, trans with oxalate, there is no reaction. So this is another way to differentiate between cis and trans isomers. Asymmetry ligands can give both cis and trans isomers. Glycinato as well takes both positions, cis and trans. This is the glycinato ligand. Stereoisomers. So geometric isomer cis and trans, let's see in the octahedral complexes. So we have here trans, because CL opposite, and here we have a neighborhood of Cl and Cl. So these are cis. And now you can see the structure is like this. It's a octahedral bipyramidal. We have here, or we could say square base bipyramids. This is in case of a trans. But in case of cis, you can see here, it's an octahedral, but the position of the chlorine is neighboring. Here is opposite. Beyond cis-trans isomers, three similar groups of complex facial, meridian isomers, and enantiomers. So if you have three octahedral, three atoms similar, and the three groups are similar. So now you have a facial. If they are neighboring, you cannot say this is a cis. Cis, you would talk about two atoms neighboring. But when you have three, you call it fac or facial. If you have opposite, two neighbors, one opposite chlorine, you can call it meridian or mir, where three NH3 ligands in one plane, three chlorine ligands in a perpendicular plane. But here are the ligands are adjacent or triangular face. So now we have more than cis and trans when there is more than two or three. So they could be neighbored or they could be opposite. We have a facial and meridian. Okay, so now we have optical isomerism, optical. So you're looking at the mirror and see the change. When you put your hand in front of the mirror, so you can see the reflection, everything will be opposite. This is the left hand. You can see it as a right. And these are identical, but different position. If you put this compound here, you can look at it in front of the mirror. You can see. So we have already two structures. One is optical to the other. So we have two compounds, similar in atoms, everything, but the position will be optical. You put it in front of the mirror, you can find the other compound. So called enantiomers, non-super impossible mirror image, not super impossible. Isomers that differ only in the way they rotate the plane of polarized light. So structures that are non-super impossible mirror image of each other are called enantiomers. So now we have cis and trans, we have fac and mir, and now we have enantiomers, which are optical. And these are called chiral as well, chiral. Structures that are super impossible are achiral. So anything with A, it means opposite. So you have a chiral, you have achiral. Enantiomers rotates the plane polarized light to the right clockwise is said to be dextrorotatory or designated plus or even D. Enantiomers rotate the plane of polarized light to the left. If they are anti-clockwise, is said to be levorotatory or designated minus. So this again is more names to be memorized that you can see there is a enantiomers, which they are optical or a mirror image. We have two mirror image, either they are superimposed or they are not superimposed. It means when you put them in front of the mirror, they will be look-alike. They look alike exactly with the position. They call it superimposed. But if they are no, there is a change in the position, they are not superimposed. So you can see this is a chiral. That's not a chiral, would be achiral, and you can take. So optical isomers mirror image are either superimposed or not. Enantiomers mirror image without not superimposed enantiomers. There are super impossible, there are not super. Enantiomers do not have a plane of symmetry. Any molecule which possesses a plane of symmetry superimpose on its mirror image. Any molecule possesses a plane of symmetry. So it means they are symmetrical to each other. Enantiomers are rotate, polarize light in different directions. Therefore, enantiomers are also termed optical isomers. Now let's see these. Rotate clockwise, anti-clockwise. Clockwise, you can see the iodine, hydrogen, bromine, chlorine. And there is a central atom. So now these ones, clockwise, we call them chiral R. If they are anti, they go with S. If you can see the change, brom will be here, chlorine will be here. Iodine and hydrogen will be the same position, but these are in different position. So rotate around central atom to change position of ligands. Now we can see mirror image here. Look, this is the mirror image. You can see chlorine beside this chlorine. This chlorine is here. Cobalt is in the middle, nitrogen down. But this position between nitrogen are opposite here in the mirror. So the image is not superimposed. It's reversed. So here, mirror image. Now let's look at this mirror image here. Is what is different as well. Or this is inside, inside, out, out. If you rotate around the y-axis, so we can see here this superimposed to this one, and they are cis. But here, trans isomers will be opposite, chlorine, chlorine. Opposite to each other, they are cis. Okay, group work, I can give you this, and you check how can you identify optical isomers and why. Okay, so you can put them in front of the mirror and see. Okay, so I solved it. Cis is optical isomer, trans is not optical. And here you have the rest as well. Stop here.